This is rational function inequalities part 2. In part 1, which was example 1, we looked at this example here. It was this rational function is less than negative 3 over 2, which was looking at where this function is below the line here, y equals negative 3 over 2. In example 2, this same rational function, I'm now looking for where it is greater than or equal to negative 3 over 2. So same function, graph the exact same way, same line, negative 3 over 2, but I'm looking for all the places where the function is greater than or equal. So again, what I'll do is I'll look from left to right at the entire function and determine which parts of the domain have it such that this function is above this value. It doesn't happen for any of these. This whole branch over here is below the line. This part is above, and 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 above, until at this point here it's equal. And we already solved for that point. We did that algebraically. We solved for the point where the rational function was equal to negative 3 over 2. That happens at x equals 0. So to answer the question, where is this function greater than or equal to negative 3 over 2? Well, it starts over here at this asymptote, which is excluded. It's not actually a part of the domain. And it happens until the point of intersection, which happens at x is equal to 0. And it's included because this allows for the point where they're equal. So the answer is x, an element of negative 4, excluded until 0, which is included. Okay. More to come in just a second. Okay, back on pause. Example 3 has the same function again, but it's asking where is y greater than this function. So there's no number here. It's just asking where is the y greater than this function. And the way to solve this would actually be less of a solving and more of a graphing. It's asking you to graph y greater than this function. And we're going to do that the same way you would graph any y greater than function, a two-variable inequality. You'd start by drawing the function itself. In this case, because it's a strictly greater than, no line underneath, I would draw the function itself with a dotted line. And because the y is greater than, I would just shade everything above the function. It would look kind of like this. Shrink that down a little bit. So I've drawn the exact same function. Remember, it had asymptotes at x equals negative 4, and at y equals negative 2. I kept in that line from the previous example. This function is drawn with a dotted line because it's excluded, and everything above it is shaded. And there's one more example to look at, another solving inequality, but a little bit more complicated. Okay, last example is one that asks where this rational function is less than this function. It's not just a number, it's not a constant linear function, but this one is a linear function. This has a slope of negative 1 and an initial value of 6. And I'm looking for all the places in the domain function where this function is below this function, less than. So again, always a good idea to sketch a graph. In this case, if I were to sketch both of these, the rational function has a vertical asymptote x equals 2 and a horizontal asymptote y equals 1. I'm drawing those branches there by plugging in a couple of points. This, like I said, is a linear function with a slope of negative 1 and an initial value of 6. Looks like that. And if I go across the domain from left to right, all the places where this function is below this function, what happens is this entire branch, it's going to be from negative infinity until the asymptote excluded. And it's also, the rational function is below the linear function from this point to this point. So there are going to be two elements to this answer. There's going to be negative infinity to the asymptote and intersection point to intersection point. But I need to find those intersection points. And to do that, I need to set this function, the rational function, equal to this function. So what I'm going to do is I'm going to take these two parts, set them equal to each other. I'm going to isolate the rational part like this. And next, to solve this, what I have to do is cross multiply. I'm going to get a quadratic. So when I do that, I'm going to get 1 equals x minus 2 times negative x plus 5, which works out to be negative x squared. That's going to be plus 5x plus 2x, that's plus 7x, and then minus 10. And the way to solve a quadratic is to bring all the terms to one side, set it equal to 0, and then probably use the quadratic formula. I'm pretty sure in this case this is not factorable. I'm going to bring everything to this side, to the left-hand side, to end up with a positive squared term, though it doesn't really matter where you move all the things. If I bring this over, that becomes plus 11 equals 0. I'm just going to align this more nicely. Okay, so this is the quadratic that I have to solve. I'm going to use the quadratic formula and come up with the two answers. And there should be two answers because there are two different intersection points. Having plugged into the quadratic formula, you find two x's. X is approximately equal to, because I'm rounding it, so I'm going to use the correct symbol, is approximately equal to, let's see here, 2.38. And also 4.62. I just use an online quadratic formula calculator. So this is what I get. I found those two intersection points, which means that the final answer, like we said, is all of this entire branch here from negative infinity until the asymptote, and then from intersection point to intersection point. So I would write that as x is an element of negative infinity until the asymptote, which in this case was 2, union. That other point was intersection point to intersection point, and because we were looking for where the function was strictly less than, I won't include either point. I'll say from 2.38 to 4.62, both excluded.